We're on chapter 6, and today we will talk further about wall slip in this lecture 7.
Questions? Okay, so we are at the beginning of discussing wall slip, and let's continue to get familiarized with the consequence of wall slip. I cannot motivate you enough to tell you that this wall slip turns out to be a problem that we must address and understand if we were to understand nonlinear polymer rheology. And it just so happened it's the wall slip is quite old concept in polymer rheology. In the discussion of general discussion of fluid mechanics, we always wonder whether we should have a no-slip boundary condition or not, since meaning fluid mechanics itself does not answer that question. It belongs to the study of the physics of that fluid. So I think there you just say, I have a no-slip boundary condition, but you wouldn't be able to develop an argument about why there isn't any slip. Wall slip, as you already start to see, is uniquely strong in polymers. So let me just bring this back to you again, that if you have slip, then your, let's see, you have this much slip. Total V is from here all the way to here. So I know I can all the way to here. There's a little bit wall slip here, and this is zero velocity there. And I'm indicated for you that if there were no slip, it would be this line, right? Instead, you have shear rate indicated by the black instead of the blue. So let's discuss some consequence of having wall slip. Last time we introduced, I know I keep blocking myself, we introduced the concept of extrapolation length. Extrapolate to 0, and you get a B like that. 0 is here, so this is BS. And today I want to first start by indicating how you speak about how much there is, how much wall slip there is. And the way to discuss that is quite straightforward. There are 3 ways you can do it. One is 3 ways. So I'm going to quantify the degree of slip, of wall slip. How do I do it? I already provided you the tools, but let's be more explicit. First way, obviously, you could think about this ratio. That should give you something unambiguous. Okay? If it's Vs over V, that should give you a measure of how much slip there is, right? Reasonable? Well, how do you do that? We know V in the symmetric form is 2Vs, there are two of them, plus what is the true shear rate producing? This gap is H, as you know. So it's this, right? So if you plug this in here, you'll realize that so basically, I'm going to divide upstairs and downstairs by V, and of course, that gives me a gamma dot over Vs at the bottom. Yeah, just plugging this in here, right? And you already know what is this. Well, that's the powerful extrapolation lens. So, since this is not a form I like, I prefer you to look at a form so, oops, isn't that what I was trying to tell you, that the ratio of B over H is a measure of degree of slip, and I claim that this ratio is also a measure of degree of slip, and obviously they are interrelated in this explicit manner, such that this approaches 1 B over H. Did I say 1? 1/2, because it's symmetric. Right? In other words, all the V's will be nothing but 2 Vs's. That's the limit. That's the limit where this dashed line will become vertical. This black dashed line, right? So that's one way. And another way, obviously, is to ask the true shear rate versus the apparent shear rate. The black line slope and the blue line slope. Blue is never quite blue enough. That one. Right? So you will find, oh, that's also very easy. Just plug in the formula. You have Vs, you have gamma dot over H. You divide the gamma dot on both sides. And you find that's nothing but 1 over 2B plus H. Of course, I forgot to write H here, because this is dimensionless. So, you get that. Again, I give you the opposite limit. When B over H is very small, this ratio approaches 1. Yeah? So that's, of course, the limit of no slip. The apparent shear rate and the true shear rate are the same in that limit. So once again, the quantification is expressed in terms of the ratio of B over H. That's it. So that's how you do it. And the what correction? We can call it rheological correction due to slip. By that, I mean correction to your measurement. So for example, you have want to measure viscosity. And viscosity, of course, is stress divided by shear rate. And since you don't have any instrument to tell you that your shear is following this blue line or it's following the black line, all you know is it's V over H, because that's what you know. You don't know if inside it is undergoing V over H or it's undergoing shear rate of gamma dot. I guess in this book, let me try to confirm it, because now suddenly you see that my gamma dot refers to something local. So I think in my book, I basically kept it in such a way that the gamma dot always means the local rate, meaning meaning even in presence of a slip. So it's the apparent rate is always V over H, and true rate is that. So so you will get an apparent viscosity, and you will find the true viscosity. You will find your experiment is in error, because you know your stress is produced by the true shear rate, gamma dot, times the viscosity of the material. Okay, so if I plug this in here, I will get eta gamma dot divided by V over H, right? By definition. Yeah, by definition, because I know whatever I measure, whether you have slip or not, I know the stress is generated by what is the actual shear rate multiplying the actual viscosity in steady state. Remember, I keep saying all this discussion right now is all done in the limit of steady state, meaning no transient. Startup has already finished all the transient behavior and reaching steady state. But this expression is what I already worked out for you here in B. So you'll find you are underestimating your viscosity by 1 over 1 plus 2B over H. In other words, it's smaller than the real viscosity that you intend to measure. So here, there were some confusions. I think I will probably have time to describe it. The confusion would be, oh, the measurement, which is always this apparent one, seems like will scale as 1 over B over H. In other words, your measurement seems to become a function of H. We'll come back to that, whether this is correct or not. Any questions? So this is just help you to develop a feel about what slip can do to mess up your measurement, to make your measurement less reliable and accurate. Keep in mind, when you do such a measurement, it doesn't have to be your dear polymers. It could be your ketchup. It could be your toothpaste. And it's in that sense, I want to come back to a comment I made in the last lecture when I said yield has never been, is a concept in its discussion that we have, has never been used for polymer rheology, with the exception that I mentioned previously as well, with the exception when a rheologist is dealing with stress, is dealing with yield stress material, such as ketchup and toothpaste. Only in that incident, yield has been invoked with the same definition that we have been using. So I just want to be clear, not to people don't blame me for misspoke. Only in that case, yield was used in polymer rheology, not otherwise, until we start to speak of it. And of course, as I told you, Bryce Maxwell also, not also, he did it first. Just nobody paid attention to it. Okay. Yeah, with a mask on, it looked like there's a little cutoff. All right. Clear? So this is just, as I said, this is just for you to first to have a sense of, if you have more slip, you better watch out. Your measurement is no longer accurate. Okay. The rest is something that I can go back to and describe for you, which is what we already did last time. B is argued to be this last time. And this is sort of like the equation. I did it in a more detailed form in the book. But in our discussion, we had it quite clearly. I argued that beta is 8-1 divided by this. And so the book didn't quite have explicit notation as I did it here for you. So we are only going to discuss the limit where you have melt. So we're only going to discuss this limit. In this limit, this eta1, which is this region where polymer chains is no longer entangled with the bulk, chains in the bulk. In that limit, this eta1 can be estimated. just a piece of knowledge that we may not have discussed many times. I mentioned before in discussion of repetition that the viscosity of a polymer is heavily molecular weight dependent when you are exceeding certain critical molecular weight. Before that, the relationship between them is linear. I'm drawing a double log plot, so the slope is the exponent. So this is indicating that viscosity here goes with molecular weight to the 3.4 power. And this strong molecular weight dependence, we even went through it. It is due to the fact the chains are having trouble moving because there are many other chains here, so they are trapped in a tube. And that's the origin of high viscosity. Well understood, no debate. Around when the molecular weight is sufficiently low, around ME, we tend to say MC is about twice ME. Around ME, the viscosity becomes very, very low. And last time I even mentioned how you can get this ratio to be a million. We're very low, such that we can assume it is really just the viscosity when molecular weight become as low as entanglement molecular weight. Entanglement molecular weight is a concept we discussed when we talked about packing model. You can always go back to the recording to find out that part. It's and certainly discussed in the book, mentioned in the recording. So it's basically when chains are just marginally long enough. It's basically closely related to this onset. It's just, oops. I should not play with this too much. You see that it's missing what I wrote. Supposedly, this should be a high-end PC and not crash like that. It crashed. You know, if you look at the recording, this part is all in there. I'm not going to be more. So basically, you can recognize that this will be the viscosity that's rather low around here. And I'm not going to go getting into anything complicated. If you like to think about the viscosity of M, it is essential, and we can let me allow myself to call this eta E. Then essentially, a polymer chain of higher molecular weight essentially is eta E M over ME to the 3.4 power. This is developed in chapter 2, but for us it's enough for us to acknowledge that this is the case. So here comes, with that you're done. You have an explicit prediction of what B is, depending on the molecular weight of your polymer melt. Which is equation 612. So I'm recognizing that if you look at the book, we are over here, we are in section 6.1. Over here, quantifying, we are at 6.2, talking about how to quantify. And here, we are really at 6.3. So this is what in our book claimed to be the maximum B that you can achieve. There's one consequence perhaps I should mention, which is to have some sense when you have corresponding maximum B, you also have a corresponding sort of a maximum slip velocity. So here's something that I think I need to bring you to speed. It turns out this is, of course, this chapter that took, 30 pages to write, is the most thorough discussion on wall slip in the open literature in one place. Usually a textbook probably have a couple of lines mentioned about it. So this part is quite thorough, and there are several things that it was not clear until I started to write it out. One of the things that was not as clear and it became more clear, and there were examples I will show you later, is the fact if you just start to shear your sample like this, you will face the question of when do you encounter maximum wall slip. This actually is something I wish you to, I need you to realize from the beginning. Number one, you probably could guess wall slip require Weisman number to be relatively large. Even WI is perhaps not the best way, but close enough, because if you shear more slowly, the black chain can always rearrange around the red chains before anything even happens. So in that limit, of course, you don't cause them to decouple. Not very strange. So WI smaller than 1 is not going to do it. However, if I say WI equals 50, is that going to give you maximum slip? Or equals 500? When does it do it? Give you maximum. Because maximum you can see is this much. So it turns out that is yet a question to answer. But at least in the limit where you have maximum slip, I'm describing here on this line, the maximum amount. I'm describing here, if you like, the red and black chains are fully disentangled with each other. In that limit, I can claim that this eta 1 reaches eta E, which is a very specific number, okay? It related to the molecular weight of your polymer at ME. Before that, you have a whole spectrum of partially disentangled interface. And consequently, just by this formula, you have B ranging from nearly 0 or nearly the value when I say 0. The minimum value is, of course, this, right? Which is very small, though, right? For our melt, we're talking about 5 nanometers here. So from that all the way to the ratio, all the way to, oh Lord, to this ratio, to the third power, or 3.4 power. So obviously, eventually, your inherent ability to slip the maximum amount is determined by how high your molecular weight is above ME. We've, in the literature of polymer dynamics and rheology, one famously called this Z the number of, I just want you familiar with this language. They always say the number of entanglements per chain. As if you have a chain this long, and this is the entanglement length, and you just count how many of them. Z. Sometimes it's known as the degree of entanglement, and explicitly we call Z the number of entanglements per chain. And it plays a role here because this thing is nothing but that ratio. So B max is nothing but Z third power multiplying a length scale of that interface. Well, having said that, I could give you a little bit of physics that if I omitted so far, that's because we haven't touched on it. That little bit of physics is that, let me just rewrite this again. Oops. See this new page? The pen is gone. It comes back. Max is M over ME, 3.4 power. Now the little bit of explicit physics, polymer physics. It turns out we went through this packing model, actually, where we introduced a concept of P, which I call it molecular molecular thickness is what I would call it. It's a sense of how thin, how thick your polymer is. So your polyethylene may be this thin, and your I know I don't want to mess up in terms of maybe I do this. Your polyethylene is this thin. Your polystyrene is this thick. I know it's probably hard for you to tell, but so that's characterized by P. And I would even go as much as telling you that P, for example, for polyethylene is 1.6 angstrom. And for polystyrene is about 3.95 angstrom. Quite a difference. Because of that, similarly, because of that, ME is rather different. For polyethylene, it's about 900. I know, I don't need this. What do I do? It's about 900 grams per mole, okay, for polyethylene. Whereas for polystyrene, it's 13,000 grams per mole. Very large, very big difference. More than 10 times. And that's a big deal. Because what happens is you can, I guess I will make that as your homework, calculate, given what I've given you here, calculate B max for PE and PS at a common molecular weight of 200,000. I can further tell you because that for you to calculate that the spacing between entanglement, for the same reason, because P is different, is about 28 nanometer for polyethylene and about 78 nanometer for polystyrene. So what I want you to, is to calculate the maximum B for these two polymers. And you will be able to make a conclusion that for PS, never mind wall slip. So you understand what I mean by this. Whereas for polyethylene, the wall slip is very severe problem. Okay. So that's sort of a little exercise I want you to do. So now we can move on to I guess before I move on, I keep looking at this expression here, which I think it was important to mention. So let me just discuss a little bit about equation 6.9a. So when you have maximum, oh Lord, and I see the pen is gone, but I can still write. What's going on? When you have, when you have, when you have a maximum wall slip, of course, there will be a corresponding slip velocity that reaches a certain maximum value. And it is not difficult to show a pretty, I think it's a pretty fascinating relationship, because we basically said Vs is sigma divided by beta. And if you are talking about maximum, then you are talking about beta being minimum. And then you are further talking about, I already know the answer, so I share with you. Then you also further wonder about what stress level are we speaking at this maximum wall slip. So it turns out the stress level is around the plateau modulus level. And the plateau modulus, just for completeness, is something that you learned by doing South measurement. By doing South measurement, you get a G double prime and G prime, and there will be a crossover frequency, which is about the reciprocal relaxation time. We mentioned about it. And the plateau modulus, PL stands for plateau modulus, is basically the level where the G prime levels off at high frequencies. Okay? So I will be able to write this as G plateau modulus. And at the bottom, I have beta. Beta minimum is nothing but eta E. And times the entanglement length. In other words, beta minimum is eta E divided by entanglement length. Since it's in the denominator, it flips up. And this quantity turns out, based on the repetition theory in chapter 2, is nothing but, obey the general form of Maxwell, that a viscosity is always going to be related to a modulus and a time scale. It turns out this time scale is eta E. Eta E is related to tau E. Tau E is related to eta E through this shear plateau modulus. And by that token, because eta is also just plateau modulus times the relaxation time, repetition time that we mentioned before. Therefore, the ratio of the two is the ratio of the relaxation time. And we have, I have introduced for you that this is 3.4. So this speaks about the origin of what is tau E. And if I do that, this equation says the maximum slip velocity actually involves some very tiny length scale and time scales. The length scale being the tube diameter or the mesh size of the network, and the time scale. Remember, velocity is by definition length divided by time. So that time scale is that tiny tau E, which is just the relaxation time of a little mesh size moving. Okay, so it's very fast. So take the ratio, that's what this is. Okay. With that, I think I'm over the formal part or the more abstract part of the discussion of wall slip. Now we can come to some, to get some practical impression of what's going on. Any questions before I move on? Yes. So, sure, yes. It's a good question, actually, Alex. I thought you were asking a more confusing question. So, of course, you are giving me a piece of a sample, such as this PDMS. So we know it's molecular weight. And of course, in reality, this sample may not be monodispersed and all that. And I keep emphasizing we'll discuss most of our results in the limit of monodispersed. In other words, if you don't have monodispersity, this does not hold, this thing. Number one. Number two, since you have nothing is ever purely monodispersed. 1.1, 1.2 polydispersity index is even good, fine enough. And there, it's always safe. You had a good question. It's always safe to think that this M is weight average, molecular weight. Yeah. I know for notational simplification, I have just been using M in this book, actually, without saying MW. But yeah. What a good point. What's the best way to answer you? I can answer you in a way that should be satisfying. The satisfying way to answer, Alex, is to say that, keep in mind that this is, if I should keep the habit of telling you what this is. I think I told you once. This is equation 612. So instead of being explicit, because this works very well only when it's monodispersed, it's written here again. It's better for you to go all the way back to the formula at the top. There, which is actually the origin. It's more original than what I further deduced later. So even for a polydispersed sample, this formula, the top one, is accurate. In other words, B is proportional to eta. However, I know I'm confusing you, but confusing you is the way for you to learn. However, keep in mind, eta 1 has a whole range of values possible. This is the mystery of it, in fact, mystery meaning. So in other words, it has to do with the degree of disentanglement you have. And unless you push it to maximum disentanglement, which we will talk about right now, right after we finish this question, unless you have that, you would not know what is your B per se. But it's useful to know what is the maximum possible. When you have full slit disentanglement, as I described in detail already here, in that limit, there's something very explicit you can talk about. And certainly in the case if it's monodispersed, it's very explicit in terms of saying how it depends on molecular weight. Good point, yeah. So this formula, this expression here, would not work so well if it's polydispersed. Because what molecular weight are you speaking about that, right? Yeah. Okay. So let's move on to something more, give you more practical impression. In particular, we will talk about, for now, just maximum slip. The question really is, how can you acquire that state of maximum slip? We call it, I know I simplified, stick-slip transition. So this is we're going to discuss a transition that is so cleanly it can be so cleanly observed in the stress control mode. So whereas a rate controlled mode is a much more complicated story that we will defer to next time. So this is a place where I can start to recall for you the capillary. I call it capillary extrusion. Basically, stick-slip transition in capillary extrusion. So that there, you remember, we just have samples in a barrel. This is all your sample, and connected to a die, and you have a piston pushing your material out of the little opening. There are really always two ways to push. You can push it with a constant pressure, or you can push it with a speed of that piston. We call this piston. We will discuss pushing it with constant pressure because, well, not only because, in the limit of having a constant pressure, we are going to be able to claim that we are applying a constant wall stress. So this goes back to when I was reviewing the capillary capillary rheometry details. There was a formula saying that the wall stress is related to the pressure gradient. See, this is the length of the die. D is the diameter of the die. Remember, pressure has the unit of stress, force per unit area. And if you recall, we talked about in the limit of Newtonian that the velocity field inside a die will look like this, with maximum velocity in the middle. And if there is no slip, you have zero velocity at the wall. So the rheometer can be built this way. In fact, the simplest way you can think about building such a rheometer, very primitively, is you put a dead weight on your piston. Okay, put a weight. Right? Just put a weight of sufficient amount. It will give you, the weight. Of course, the area will be this area actually. Whatever circular this reservoir could be circular cylinder. So you will be able to exert a pressure of enough amount. So it was. You need no electronics in that limit. You need zero electronics. I don't have a motor. I just have a dead weight. Pushing it down, and I know material is coming out. And we even know in the Newtonian limit, the amount it comes out is related to the shear rate at the wall, which means I can speak about that. They are all related because it's a Newtonian limit. So I can see how much material coming out per unit time. I will be able to, in turn, determine what is wall shear rate. So this actually was what was done. It was done in 1958 for polyethylene by Bagley, using such a pressure control rheometer. And he showed absolutely the first data of its kind. I presented this, reproduced this data as figure 6 point. One of the very few literature figures I reproduced in the book. So what you do is you just load up your barrel and you exert certain pressure and see how much material comes out. So you plot that, how much material comes out at one pressure, and then you do that at another and another. So this is the pressure. And he finds that there is a critical pressure at which it jumped. It's absolutely remarkable. It jumped, and if you can continuously lower your pressure, you find that this polyethylene will remain in this high throughput state until some, I don't know, in my book I call it the pH. Basically, this is a feature of hysteresis. So I know I'm not lining up this point very well. Yeah, there's critical pressure. And this jump, in his case, it was about 10 times. Okay, so this jump is about 10 times. So we typically, in rheology, like to use double log. And I try to preserve his original data. He was presenting in the log scale. Okay, so he is not alone. Later in the 70s, a Russian group, we know Gradov, got hold of lots of monodisperse polyisoprint type of material from his colleagues and did similar studies. And this is presented in figure 6.5. Their interpretation was a little bit strange, I have been in contact with the younger colleagues of Vinogradov, trying to figure out exactly their terminology. Basically, they observe something similar. Okay? Basically, you have something that makes a transition. And they tend to call this a fluid to rubber transition, which is very confusing terminology. And in fact, is entirely misleading. There's no transition in the bulk because, in fact, now I recall that they think this transition has to do with the bulk constitutive property of the polymer. And they did recognize that at this point, if you translate this to stress through this formula, they did find that this level of critical stress is at the same order as the plateau modulus. So that inspired them to speculate incorrectly that this is a bulk property. Okay, this is a pretty explicit history that that I have been directly involved with in terms of communicating about such early times about what all this means. They did not report hysteresis loop. Exactly. I wonder at what point I will say anything about. Let me come back to it. It's the matter of hysteresis and the matter of this interpretation being exhibiting. In other words, what is making a transition, makes such a big change? If you like, what happens is near a critical pressure, all of a sudden the material become 10 times or even 100 times. When he does rubber, he can find 100 times. We later could find 1,000 times faster. No sweat. At the same pressure, all of a sudden, the material initially was coming out slowly, then immediately come out much faster by many order magnitude. Is that what's happening? Since I have this figure. Is it because of what's happening in the bulk? You see, this is the bulk, right? Anything away from the surface is the bulk. Is this material, a majority of this material, undergoing some magic change or not? That was not clear as late, I will come back to it again, as late 1990s. It was not clear. I will get to the story of this. I see my book made effort not to speak about that. So this part is a bit like what I have been complaining about textbooks, right? The textbook just shows the result. It never talks about the controversy, the debate, when it becomes something clear to everyone. And at least for this little part, because I had colleagues in polymer engineering who initially were from Russia. So I try not to, I try to be nice. In any case, I will probably make a section. I know today is running out of time. We'll probably make a section next time to talk about a little bit of this history. So in any case, I'm reaching near the end. We picked up the topic. This color is fine. We start to pick up this topic, indeed, in the mid late last century, and for example, figure 6.6 is our figure now. Since there were controversy about what is the nature of this transition, we got into the game, and next time we can describe how one can very straightforwardly indicate about the nature of this transition, and I think, let's see. I guess I only have to indicate. So I know this is all kind of, let me just use the remaining few seconds. It's all kind of me talking, but I think this part is quite useful for me to just indicate the figures in the book. So this is the first figure, Bagley. He saw his traces, and this is the figure from Russia, Vinogradov's group, showing. With the figure, now I can make a comment. Both of these two, I try to preserve their way to do it. It's log scale on the vertical axis, on the y-axis. I will advise my student never to plot as they did when you plot log scales. Look how they do it. You take your number, you make a log scale, and then calculate what that number is. In other words, this is almost like presenting the exponent to the 10th power. Okay, so if I tell you, if I ask you, Alex, what is the value at here? You won't be able to tell very easily. I know, I guess I'm teasing myself here now. I know you cannot tell here either because I didn't give you the mini scale, but the next one did. This is the way to do log scale. Never any other way. Never. Folks, right? This is just for any of you who are doing science. Because I can tell, oh, this is 0.1, actually this is 0.2, 0.3, 0.4, 0.6. I can read all of them. Not this. I just, why you do that? Because maybe the graphic software, they don't have it at that time. Maybe. When I was doing PhD, I was telling guys, when I was doing PhD, our publication, all the figures, you send to somebody, draw it, and take a photo of it, and then send to the journal. Just unthinkable. Many of our papers were typewritten by secretary, okay, in our time. Not so long ago, as if it was yesterday. In any case, so that's this. I apologize, I don't have the mini scales, but I do it the right way. So this is polyethylene. We have this result. I just want to show you, look at this. How many order magnitude jump? 10,000. This is a 10,000 time jump. All it takes is for you to get out of a high molecular weight. Right? From 0.1, did I say 10,000? Sorry, it's about 1,000, right? Yeah. There was higher one, but this one is 3 order magnitude. But that's just incredible. So it all comes because you are initially in a untangled state, so your B is negligible compared to, the only thing I haven't said about any of this, which we have to do it next time, is how to calculate this jump. No slip. Well, it turns out it's A times B over D. D being the diameter. And I claim that this B is maximum B. So you can see a factor of 1,000 means B is about 100 D, right? Because 8 is a factor of 10. And diameter D typically is a millimeter, so B become 100 millimeters. It all has to do with how much molecular weight you have, so that you could have, you could have a much larger value here. Okay, any questions? I think I'm over again. All right. We are done.